let's talk about how to do these calculations, energy and heat capacity. So this is the equation. The heat that's transferred will equal the mass of the substance times its specific heat capacity times the temperature change. Okay, temperature change is delta T, and it's always T final minus T initial. So delta T is the change in temperature, the final minus initial. We're going to do a lot of calculations like this in lab this afternoon, and it's important to get those straight because sometimes the change in temperature is negative. The change in temperature is negative if the temperature goes down. It's positive if it goes up. Heat can be negative or positive. Heat leaving is negative. Heat coming in is positive. And so we have to pay attention to those signs. We also need to make sure that our units work out. Usually Q is in joules. The mass is going to be in grams. The specific heat capacity will be in joules per gram degree Celsius, and the temperature will be in degrees Celsius. So here's an example. It's a very long example. These questions tend to be long. So you find a copper penny, pre-1982, in the snow, pick it up. How much heat is absorbed by the penny as it warms from the temperature of the snow, minus 5 degrees Celsius, to the temperature of your body, 37.0 degrees Celsius? Assume the penny is pure copper and has a mass of 3.10 grams. You can find the heat capacity of copper in table 3.4 on page 74. How's that for a long problem? So read through the whole problem. I know a lot of you find questions like this very challenging just to figure out what am I supposed to do. If you could just give me the math equation, I could solve that. But this whole word business is not good. So I'm going to try to walk you through that. So the pre-1982, that is a number, but hopefully you recognize maybe that's not a number that's going to show up in the calculation. The only reason they stuck it in there is before 1982, pennies were made out of pure copper, and after 1982, they had a zinc core with a copper outside. So they were not pure copper. So that's just a little kind of background information in there. There's these other numbers. We have minus 5 degrees Celsius. That's a temperature. Here's another temperature, 37 degrees. And then here we have a mass. Now, even if they don't tell you this is the mass, you should be able to recognize the mass from the unit. Gram is a unit of mass. Degrees Celsius is a unit of temperature. So we've got two temperatures. And if we think of that equation, Q equals MC delta T, we need to find 3 of the 4 variables in that question. So here we've got the mass, and we've got 2 temperatures, which will allow us to find delta T. The thing we're missing is the specific heat capacity, and it's basically telling us, go find it yourself. So let's go back to that table. Over here, copper, there's copper. Here's the specific heat capacity. So a lot of times they're going to make you look these numbers up. So 0.385. So, yeah, this one's challenging because there's not really much room to write on this little screen. So 0.385. And I don't think I'll write in pink today. That was yesterday. So the information that we have a temperature. What's the initial temperature of the penny? What does it start out at? Minus 5.0. There we go, degrees Celsius. What does the temperature of the penny end up at? 36.0 degrees Celsius. Okay, and it's okay to draw yourself pictures if you need to. Sometimes that really helps. Question? Oh, it's 37. Thank you. Yes. I was testing you. No, I was just Yeah, there we go. Is that better? Yeah. No, I just made that up. Don't do that. Okay, so there's the final temperature. Sorry, not trying to be confusing, but... And then the other thing is the mass, 3.10 grams. And then we looked up the specific heat capacity of copper, 0.385. The units on that, joules per gram degrees Celsius. So those are the numbers that we have, the information. And we got those, the ones on the left out of the question, and the one on the right we had to go and look up. Okay, so move up here. The equation that we need is Q equals MC delta T. So we've got M and C. We're trying to find Q. It's asking how much heat is transferred, and we need delta T. Let's go ahead and calculate delta T separately so that it just makes things a little simpler. So delta T is the final temperature minus the initial temperature. The final is 37. The initial is minus 5. Got to be careful with your negative signs. And so that comes out, I'll show you, I think I have room over here. That comes out to be 42, right? Yeah. Sorry, blanking on my math. 42 degrees Celsius. Use your calculator. So now Q equals, and we're going to plug all those numbers in, see if I can remember them, 3.10 grams, 0.385 grams per, no, that's not right, is it? Joules per gram degrees Celsius. And the change in temperature, 42.0 degrees Celsius. Bless you. Calculator time. 3.1 times 0.385 times 42 equals. Calculator says 50.127. Did I do that right? Now let's double check our units. Grams, cancel grams. Degrees Celsius, cancel degrees Celsius. And what I have left is joules. And that's good because joule is the unit of energy. And then we have to think about significant figures. How many significant figures does each of the numbers we multiplied have? They each have 3. 3.10 has 3. 0.385 has 3. And 42.0 has 3. So our answer should have 3 significant figures. We're going to chop it off there. The next digit is 2. And so we call this 50.1 joules. Like I've mentioned before, I'm going to use significant figures throughout the class, and in the homework cares a great deal about significant figures, doesn't it? So on exams, I will not intentionally try to trip you up on significant figures, but you should, just give it your best shot at doing significant figures all the way through the class. Any questions about this problem? So here's another one. We're going to do a couple of them here. So again, read through the problem. When 56 joules of heat are added to 11 grams of liquid, its temperature rises from 10.4 degrees Celsius to 12.7 degrees Celsius. What is the heat capacity of the liquid? So let's highlight these numbers. We've got 56 joules and 11 grams, and we've got 2 temperatures here. So let's now write these down and identify what they are. 56 joules. Joule is a measure of what? Heat, right? And what's the letter, the variable that we're using for heat? Q. Okay, so that's Q. I don't know why it's Q. H would make more sense, wouldn't it? 11 grams. Gram is a unit of mass, right? So this is M for mass. And then we have two temperatures here. We have 10.4 degrees Celsius, and we have 12.7 degrees Celsius. So these are both temperatures. We have to decide which is initial and which is final. Well, it rises from 10.4 to 12.7. So 12.7 is the final temperature, and 10.4 is the initial temperature. So this is how you figure out problems like this. And then what are they asking us to find? C, the heat capacity. Whoops. So we need that equation again. Q equals mc delta T. But we need to rearrange this so that C is by itself. We're going to do that by dividing both sides by the things we don't want with C. If we divide this side by M, the M's will go away. And if we do that to one side, we have to do it to the other. And I'm going to divide by delta T, so those cancel out. And then I have to divide this side by delta T also. So the equation I have here is C equals Q over M delta T. Not writing small enough here. Let's find out what delta T is. Delta T is the final minus the initial. 12.7 minus 10.4. That's 2.3, right? Degrees Celsius. So I'm going to write this up here. What's Q? 56, right? So C equals 56 joules divided by the mass, 11 grams, times the change in temperature, 2.2 degrees Celsius. 2.3. I was testing you. No, just... My husband calls that a brain fart. A lot of flatulence today. So on your calculator, 56 divided by 11 divided by 2.3. If you want to multiply those guys on the bottom, you have to use parentheses. Otherwise, you're going to end up with the wrong number. So we get C equals, how many significant figures should this have? 2. 56, 11, and 2.3, they all have 2 significant figures, so we're going to round this off to 2. I get 2.2 is my number. And the units, none of those units cancel out, do they? So the units are joules per gram degree Celsius. Any questions? Mm-hmm.
What's the negative key? Like if I want to type in a negative number?
So with this equation, Q equals MC delta T, there are 4 variables, Q, M, C, and delta T. They'll give you 3 of them, or you might have to go look one up, and ask you to solve the 4th. It could be any one of them. So we've solved for C and we've solved for Q. Let's see what the next example is. I think there's one more example here. Okay, so this is solving for a final temperature. So a lead fishing weight has a mass of 75 grams. absorbs 146 calories of heat. If its initial temperature is 47 degrees Celsius, what is its final temperature? This is the trickiest of these problems. So again, let's identify all these numbers. 75 grams, 146 calories, 47 degrees Celsius. So 75 grams is what? The mass. And 146 calories is what? Is that the specific heat? Is it the temperature? It's Q. That is the heat. And then 47 degrees Celsius, well, that's obviously a temperature. Is that the initial temperature or the final temperature? That's the initial temperature. We're trying to find the final temperature, right? What else, what other piece of information are we going to need in here? We're going to need the specific heat capacity. Anybody remember what the specific heat capacity of lead is? 0.128, thank you. 0.128, and the units are joules per gram degrees Celsius. So we need to find the final temperature. Our main equation here, Q equals mc delta T. Well, T final doesn't show up directly in that equation, does it? But there is a T in there, delta T. If we knew what delta T was and were given initial T, could we find the final temperature? Yeah, we could. So what we need to do is we need to solve this equation for delta T. So we're going to divide by M and C, so those guys cancel out. If we do it on one side, we have to do it on the other side. It's like dealing with little brothers. If you give one a cookie, you have to give the other one a cookie that's exactly the same size, right? Or you hear about it. So our equation then is delta T equals Q over MC. Okay, so let's be a little bit proactive here and look ahead. Do you see any conflict or potential problem with the units that we have? Calories and joules are not going to cancel out, are they? So we can save ourselves a little grief later on by converting from calories to joules right now. So calorie, we want to go to joules. We need to divide by calories. Calories go away. The relationship is that 4.184 joules equals 1 calorie. And that's, a constant. It's in a table. It's in the back of your textbook, all those good places. And so the calculator tells me that that is 610.864 joules. How many significant figures should that number have? 3. 146 has 3 significant figures. It's a whole number, but not all whole numbers are exact. So what I'm going to do is I'm just going to underline that third digit to remind myself that's the last significant figure, but I'm not going to round it off just yet. And in lab this afternoon, I want you to keep some extra digits. Do I absolutely have to keep all of them? No, but keep 2 or 3 at least until your final answer. Otherwise, you'll get rounding errors. Okay, so let's change color here to try to make this a little clearer because it's getting kind of crowded in here, isn't it? Now we have the pieces that we need to solve for delta T. So delta T equals Q, I almost did the 146, 610.864 joules, and that's the last significant figure, divided by the mass, 75 grams, and the specific heat capacity, 0.128 joules per gram degrees Celsius. So 610.864 divided by 75 divided by 0.128 equals, I get 63.63, and it goes on. But how many significant figures should this answer here have? 2. The number in the top has 3 significant figures. We underlined that. The numbers in the bottom, 75 has 2, and 0.128 has 3. So this one should stop here. So I ran out of room, but it's okay because I don't really need the rest of those guys. I'm still carrying some extras. That's not our final answer, though, is it? That's the change in temperature. So we have to go up at the top now. The change in temperature equals the final temperature minus the initial temperature. How do I get final temperature by itself? I add the initial temperature to both sides. Ti minus Ti is 0, and those go away. The final temperature then equals the initial temperature plus the change in temperature. And that makes sense, doesn't it? We started at this temperature. We know what the change is, so we add them together. Initial temperature is 47, and the change is plus 63.63. So 63.63 plus 47, and the calculator says 110.63 blah blah blah. So this had that was its last significant digit. So 47 and 63, they both have uncertainty in the ones place, and so we're going to round our answer off to the ones place, and that's going to round to 111 degrees Celsius. And I'm sorry that's all cramped together. Can you read it okay? Any questions?
Yes.
Okay.
I'm not sure exactly what I'm doing wrong, but the delta T equation, when I put it into my calculator, I get a different number than you every single time.
I think what's happening is you're accidentally multiplying by 0.128. So then here are these chapter and review slides. These are helpful for reviewing for an exam. Just kind of give you a highlight of what we talked about in the chapter, different words that you should know. And then chemical skills. This is what you should be able to do. You should be able to identify chemical and physical changes. You should be able to convert energy units. You should be able to do these energy and heat capacity calculations.